So, another property or another matrix that we need to look into is the transpose of a matrix. The transpose of a matrix is formed by writing its columns as rows. For instance, if A is the m by n matrix here, then we would have to write these as the rows, and it will be denoted by A with an exponent of t is the n by n matrix that would be like this. Let's have a very specific example. So, we are asked to find the transpose of each matrix. For letter A, we have this column matrix, and to find A transpose, all we need to do is write the column matrix as a row matrix to A. That's it. For B transpose, we would have to write its column as a row. So, instead of 1, 2, 3, I'm going to have 1, 4, 7. Then in this order as well, 2, 5, 8. And finally, 3, 6, 9. So this is B transpose from the original matrix B. Pause the video and try to see if you can find C transpose and D transpose. Alright, so for C transpose, we're going to have 1, 2, 0, 2, 1, 0, 0, 0, 1. While for D transpose, we're going to have 0, 2, 1, 1, 4, negative 1. Now, if you would notice, our C and our C transpose is actually just one and the same matrix. Now, since that square matrix is equal to its transpose, we call that square matrix a symmetric matrix. So, a matrix A is symmetric when A is equal to its transpose. That is the definition of a symmetric matrix. From this definition, it should be clear that the symmetric matrix must also be a square matrix, because if you're going to take a look at the other examples, A and A transpose have different sizes. B and B transpose have similar sizes, but because B is a square matrix. For D, which is not a square matrix, its transpose has a different size. So there. Also, if A is equal to that matrix is a symmetric matrix, then the entries are just equal to each other, provided they are not on the same position 1, 1, 2, 2, 3, 3, row 1, column 1, row 2, column 2, and so on. So, what are the properties of the transposes of matrices? If A and B are matrices with size such as the given matrix operations are defined, and C is a scalar, then the following properties are true. First, finding the transpose of a transpose gives back the original matrix, which is kind of self-explanatory, right? Now, the transpose of a sum. If you want to find the sum, or rather you want to find the transpose of the sum of two matrices, it would be the same as finding first the transpose of each matrix, then adding them up. If you want to find the transpose of a matrix multiplied to a scalar, that would be the same as getting first the transpose of the matrix, then multiplying the scalar. Lastly, if you want to find the transpose of the product AB, that would be the same as finding first the transpose of each matrix and multiplying first the B transpose, or the transpose of the second matrix, to the first one. Remember, the order of multiplication is reversed when forming the transpose of a product. That is, the transpose of AB is B transpose A transpose, and is usually not equal to A transpose B transpose, because as you might have noticed, when we do the transposition and they're not a square matrix, the order, or the size rather, the size of the matrix would usually change. So let us show that A B transpose and B transpose A transpose are equal given these matrices. Pause the video and try to see if you'll be able to do this one. So let's first do AB transpose. Therefore, we'll first find the product of AB. A and B rather. There you go. This is A and this is B. Then we'll find the transpose of that. So, finding this one, multiplying this two, which I will leave to the viewers, we're going to get the matrix 2, 1, 6, negative 1, negative 1, 2. Finding the transpose of this matrix will lead us to the 2 by 3 matrix 2, 6, negative 1, 1, negative 1, 2. Let's see if it will be equal to B transpose A transpose. So B transpose will be 3, 1, 2, negative 1, 3, 0 there, multiplied 2, 2, 1, negative 2, negative 1, 0, 3, 0, negative 2, 1, transpose. So therefore, when we transpose that, we're going to have 3, 2, 3, 1, negative 1, 0. There you go. While multiplying that to the transpose of this one, 2, negative 1, 0, 1, 0, 2, negative 2, 3, 1. And this will actually give us, after doing the multiplication, 2, 6, negative 1, 1, negative 1, 2. So, we have this as proof that they are equal. So, hence, we can then say that AB transpose is equal to B transpose A transpose. There you go. Now, for the matrix A, given 1, 3, 0, negative 2, and negative 2, 1, we are asked to find the product A transpose and show that it is symmetric. Pause the video and try to see if you'll be able to answer this one. Alright, so first we are asked to find A transpose. So that would mean we need to multiply A, this matrix, to its transpose. 1, 3, 0, negative 2, negative 2, negative 1, transpose. This would then be 1, 3, 0, negative 2, negative 2, negative 1, multiplied to the matrix 1, 0, negative 2, 3, negative 2, negative 1. Performing this operation, we're going to have the following matrix. 10, negative 6, negative 5, negative 6, 4, 2, negative 5, 2, 5. Now, as you might have noticed, if we're going to look for the transpose of this matrix, let's just roll it down there, the transpose of this matrix is just actually the same. Because look, this will become 10, negative 6, negative 5, negative 6, 4, 2, and this is negative 5, 2, 5. Therefore, we have shown that A transpose is symmetric. And those are the transposes of matrices.